last time. Yeah, this is a last lecture. We compute the quantum dimension, and in the last lecture, we mentioned that we defined this so-called unitary fusion category. We say that this unitary fusion category is a theory, or you can say a field theory, that describe a one-dimensional excitation, one spatial dimension excitation. Okay, so then this comes a question. If that's really true, means that can we really find a one-dimensional local lattice model such that this lattice model have an excitation which described by this unitary fusion category? The answer is no. So actually we do so much and for nothing. Oh, seems. So this abstraction to find a one-dimensional lattice model is called anomaly. So anomaly, so we say this unitary fusion category anomalous. Means we cannot find any one-dimensional lattice model which is realized, which produce excitation described by unitary fusion category. Actually, it's not quite true that there's one unitary fusion category which is not anomalous, which is realizable, but that one is a trivial one. So any non-trivial one is not realizable. So the reason for this, actually, there's a motivation for this. Is this relation between remotely detectable and realizable, or another way to say anomaly free. When you say anomaly free, means realizable by the lattice model in the same dimension. So there's a belief, this is conjecture, that there's belief that if every excitation can be probed by, can be detected by other excitation via some remote operation, then this category is realizable or anomaly free. And this remote operation is something like a braiding. Say, suppose we have a excitation here, and we want to use another excitation to probe it. We can just braid this second excitation around the first one, far away, never touch, never come close to the first one. So therefore, if every excitation can be detected by this way, then we say it's remotely detectable, or we say it's anomaly free. And now we see that in one dimension, we cannot do that because dimensionality, when you have 1D excitation, we cannot do this kind of braiding or maybe some similar remote operation. And so therefore, all the non-trivial unitary fusion category are anomalous, except the trivial one. And so therefore, there's no 1D lattice model realize this unitary fusion category. And then we believe that for any gap system, the excitation always described by unitary fusion category. And only the trivial one is realizable. So therefore, in one dimension lattice model, we only have a trivial topological order. And this, again, something we believe. There is no non-trivial topological order in one dimension. And this sounds strange because there's a lot of 1 plus 1D or two-dimensional TQFT. They classify Fubini algebra. So there's many papers study that. So that kind of TQFT actually do not correspond to topological order in condensed matter sense because they are unstable. They are not a stable phase. And so the statement here is that this 1D TQFT or 2D TQFT are really correspond unstable, not really correspond to topological order. Non-trivial topological order only appear in higher dimension, not in one dimension. So in higher dimension, and we can still do fusion because we can put a higher dimensional excitation on a line than we can do fusion. But then we can also do braiding. That's one extra thing we can do. We can also do braiding. And in particular, we have a double braiding. The double braiding is like a mutual statistics. We move this one excitation all the way around another excitation. It's called double braiding. And this double braiding in physics is called mutual statistics. So when you move one excitation around another excitation, you get a phase factor. Okay. So this phase factor is theta ij, depend on this excitation I and j. So the theta ij is a phase factor mutual statistics between I and j excitation.
Sorry, Xiao-Gang,
Yes.
why do you restrict this product of our matrices to be only a phase factor? Why can't it be some more complicated matrix?
Yes, and so the reason is that this ij is assumed to be a simple object. They assume to be stable excitation.
Sure.
If they assume to stable excitation, so yeah, this became just a phase factor.
Well, why can't it be something more complicated, more non-abelian? Who knows?
Yeah. Okay. So here there's a little bit more non-abelians here. Let me explain.
Mm-hmm.
Actually, this phase factor is not just depend on ij, also depend on when ij fuse into something k. You know, ij can fuse into k1, k2. Then depend on this different fusion channel, the phase can be different. And that's only little bit non-abelian thing. So it's diagonal matrix, and there's no off-diagonal element. And so therefore, this phase factor actually have three index ij and k depend on the fusion channel of I and j.
No, I still don't believe you. I think Anton was right. Why can't a single anion appear with multiplicity in the fusion?
Yeah, they can, but this assumption is that ij are simple object. Here I assume
but k
ij,
doesn't have to be. You could have two copies of the same k, and then you could have a 2x2 matrix.
Oh,
no?
Yeah, sorry. Yeah, that's right. Okay. If a k is a several copy, yeah, then this can be a 2x2 matrix. Yeah, I'm sorry. Yeah, this is a let me see. And then this 2x2 matrix, it can be diagonalized.
Yeah, maybe you can still diagonalize. Yeah. So maybe in some basis it's still going to be like that. Okay.
Yeah. So so it's related to this thing that we talk about the topological spin. So this phase factor and topological spin are related in this fashion. So actually, if you know the topological spin, we know the mutual statistics. So actually, there's for the simple braiding, this is the R matrix. So I will not go into this in detail because time constraint. And just say there's R symbol, there's F symbol, and then there's a consist condition. And if you have N and F, we get the fusion category. If you have N, F, R, then we get the so-called braided fusion category. So that's the very simple way to understand this braided fusion category. And the braided fusion category is supposed to describe excitation in two-dimensional topological order. So here, let's give you some example. Simplest braided fusion category have two objects, identity trivial object and E. They both have a quantum dimension 1. They both are boson. And this have a formal name. It's a repetition category of Z2. It's a symmetric fusion category of this rep Z2. And there are other thing like this. They have Samian model. We have two objects, both with identity quantum dimension, but the non-trivial object have a spin, a quarter, that's a Samian. And this realized in the bosonic quantum Hall states. And then we have a Fibonacci topology order, where again also two objects. The quantum dimension is this Fibonacci number. The spin is 2/5. And this Z2 gate theory is what we discussed, the EMF. And we have the one fermion, and we also discuss stringnet. Stringnet actually is a double Fibonacci. It's like a two copy Fibonacci together, and it's a Fibonacci and anti-Fibonacci. So this is like a double Fibonacci. The stringnet example we discussed. Okay. So the first example here is anomalous. because this E particle cannot be detected by any other particle, either one or E. Okay, so we already say that the braiding is degenerate. Okay, and so this is characterized by the Mugler center, or more generally E2 center. That is this E2 center is a set of anions that have a trivial mutual statistics with everything else. Okay, if the only anion with trivial mutual statistics with everything else is a trivial particle, then this we say is a non-degenerate, or it's modular, or it's realizable, or anomaly free. Okay, so this Z2 center is trivial, is an anomaly free condition or realizable condition. And all these other, for example, are modular, and their Z2 center, Mugler center is trivial. But this one, the Mugler center is self, so it's non-trivial. So this one is anomalous, not realizable, and those are realizable. So this led to this conjecture that this unitary modular tensor category, where Z2 center is trivial, classify the two-dimensional topological order. But actually, it's not quite true. There's a little bit of mismatch here. It's actually this unitary modular tensor categories do not classify 2D topological order, but classify 2D topological order up to this invertible topological order. So there are some topological order whose excitations are trivial. So they call the invertible topological order. So invertible topological basically means that when you have a stacking A topological order and B topological order stacking together, you get the C topological order. Invertible one is that if A is invertible, that means you can find the B such that their stacking give you C, which is a trivial, the trivial product state. Via stacking, you can obtain trivial product state. Then that's invertible. And invertible topological have only trivial excitation. They do not have a non-trivial excitations. Okay, and their topological partition is a phase factor. Okay, so using unitary modular tensor category only classify excitations, but the invertible one have a trivial excitation. So they can overlook that. But if you quotient out invertible one, then we believe there's a one-to-one identification. So so using this idea, we can get a list of unitary modular tensor category, which is also a list we believe is a two-dimensional topological order up to the invertible ones. And on this list, say we have this Z2 gauge theory, which is here. This line is a Z2 gauge theory, and the double Samian model, we discussed before, also appear here. And the double Fibonacci is here. This one is a stringlet double Fibonacci, and etc. Okay. So then we can apply this idea to higher dimension. So in higher dimension, we can also think about maybe we can classify topological order by classify their excitations. But in higher dimension, the excitations are described by so-called fusion N category. There's a higher category. So this fusion N category actually is a following. The object in the fusion N category corresponds to co-dimension one excitation. So here's a two-dimensional example. This string is the object. So that's a fusion 2 category. String is the object. Then the one morphism in the fusion N category is a domain wall between strings. So that's connecting two different strings. That's a one morphism, domain wall between strings. And there's special domain wall between trivial strings. And that's in physics we call one point-like excitation. Okay, this domain wall between same trivial string is a point-like excitation. And then, however, there is also a string excitation, which are connected to the trivial string. Actually, this is called condensation excitation and or descendant excitation. They are kind of trivial, and I will not spend time on that. And but this is one of a special kind of excitation. And this fusion category, fusion 2 category, actually already contain information for braiding, because we can do a vertical fusion, we can fuse 2-domain wall, and we can do horizontal fusion, fusion 2 strings, and the consistent condition between vertical fusion and horizontal fusion can generate the braiding of these point-like excitations. So the braiding is already contain the consistency of a fusion 2 consistency. Okay. So and as before, the unitary fusion N category and the topological order is not it's not just one-to-one related. Their relation a little bit more complicated. To describe their relation, we can consider there's a map from a realizable topological order on the lattice to the fusion N category. And this map physically just means every realizable topological order have excitations, and their excitations are described by fusion N category, and that's basically generates this map. But this map is not subjective. So the image of this map is defined as an anomaly free fusion N category, means realizable. The image of this map means those fusion categories are realizable by lattice model. The kernel of this map is happen to be invertible topological order. So therefore, up to invertible topological order, we can use this anomaly-free fusion N category to classify topological order. Any questions? Okay.
Yeah, Alex, I'm not sure. Did you have a question or? Yeah, let's continue. If there are questions, please either unmute yourself or raise the hand. Thank you.
So so right now we try to use this fusion N category to classify topological order up to invertible one. Invertible one is pretty well understood. So up to invertible one, what is fusion N category, which can classify topological order. So here we see that we need to find a subset of fusion N categories. Only some special fusion N category can correspond to a realizable topological order. And so to find this subset is the following thing. Actually, when I say realizable, I'm using this so-called microscopic definition, using a lattice model to define realizable. And but when you try to find a subset, we are looking for some macroscopic properties, and which can apply to fusion N category. So we want to translate this anomaly-free, defined microscopically to an anomaly-free defined macroscopically, and we have did that. We have done that for the 2-dimensional topological order. It's an E2 center, and I was told that this E2 center can also be found on the fusion N category, but it's a physics things is more complicated, so I will not go into that route. So here to identify this fusion, this anomaly-free fusion N category, this special class fusion N category, which can be realized by lattice model, we use so-called boundary bulk relation. Okay, so we already say that anomaly or gravitational anomaly means that abstraction to be realizable. Okay, but the question is, what is this abstraction? Okay, to understand this abstraction more explicitly, we notice the following thing. Although this unitary fusion category describe a 1D excitation, in a sense they kind of locally consistent, but they are not realizable, means that they are not globally consistent. So this not globally consistent means this anomaly. But there's still some consistency. And this local consistency ensure that actually this unitary fusion category can be realized at the boundary of a 2-dimensional topological order. So that's really a boundary bulk relation. Okay. For example, yes.
Xiao-Gang, I have a naive question. So You say gravitational anomaly. Is it in some way related to the notion of framing that you?
Yes, it's one of them. But what I have here is more general. So I will come back to this point.
Okay.
Yeah. So, but here, the gravitational anomaly have been studied before, and but here I'm really presenting a more modern point of view. I will review the old point of view maybe a little bit later. So here we say that not realizable means anomalous, but they are realizable as a boundary. Okay. For example, this Fibonacci fusion category, this phi effect became 1 plus phi. Actually, it's realizable as a boundary for this two-dimensional stringlet wave function. Actually, there's this stringlet wave function have a particular boundary, and the boundary excitation happen to be described as a unitary fusion category. So this really gave us this triangle. Actually, we already see this triangle in this morning's talk. That given a unitary fusion two category, we have this wave function, which using this data, we can design a two-dimensional stringlet wave function. So this map to 2D wave function. And also this unitary fusion category also can be viewed as a description of a one-dimensional excitation. And the boundary of this wave function happen to reproduce this boundary, this 1D excitation. Okay. So from here, we can see that the different type of anomaly really correspond to different 2D topology order. So it's really that the non-trivial bulk topology order is related to the gravitational anomaly at the boundary. Okay. So in higher dimension, this idea we kind of propose this idea also works in any dimension. So in higher dimension, we have so-called the potentially anomalous topology order. Basically means a fusion N category. So in general, a fusion N category is it's not realizable, but maybe we call this anomalous topology, may not be realizable. Okay. And anomaly-free topology order means a realizable topology order. Actually, it's a boundary of trivial product states. Because when you have a trivial product state, the trivial product is not connected. You can remove the bulk. Okay, trivial product states the bulk can be removed, and you only have a pure boundary states. So therefore, the boundary of trivial product states means realizable at the boundary alone. So realizable at one lower dimension. Okay. So from here, we can see that anomaly-free means their bulk is a trivial. Anomalous means their bulk is a non-trivial topology order. Okay. And there's a conjecture, the holographic principle topology order means that the boundary uniquely determine the bulk. Okay. So when you have a topology order with a boundary, actually, if you know the boundary, then you know the bulk uniquely. Okay. So here we say that the boundary is a fusion N category. Okay. The bulk is anomaly-free topology order. Okay. So there's a connection between fusion N category and the bulk. But the bulk topology order also described by some kind of category, which actually is a braided fusion category. Okay. So this mathematically, this principle means that there is a functor we call the Z1 center actually. The map the NA fusion N category to the braided fusion N category. And this braided fusion category actually is a non-degenerate. So their bulk is a trivial. Okay. So this is anomaly free. Their bulk is a trivial. Okay. So this boundary bulk relation really tell us what is the gravitational anomaly. You know, before we say gravitational anomaly is something is abstraction to have a realization in the same dimension. But here we can say in more detail that the gravitational anomaly actually is almost equal to the topology order in one higher dimension. Okay. Similarly, this Tohuf anomaly or symmetry anomaly is SPD order in one higher dimension. This SPD order is discussed in the Zhengchen Gu's talk yesterday. So therefore, using this boundary box relation, actually we can obtain the classification of anomaly-free topological order. Means that a realizable topological order in n dimension can be classified by the unitary fusion n category, which satisfies this condition, means they have a trivial bulk. Okay, and this trivial bulk is really anomaly-free condition or realizable condition, and certainly this classification is do not see invertible one, so it's only up to invertible one. Also, I want to say that there's another condition. This unitary fusion n category should include all condensation excitation, and this is the importance of this condition is pointed out by Galta and Johnson Fried, and I think Johnson Fried probably will discuss that this Friday. And so because gravitational anomaly is so important, so let's spend some time on anomaly. So usually a gravitational anomaly is defined as an abstraction to have a nice path integral. Means that usually when you have a action, this action are diffeomorphic invariants. But however, using this action to define the quantum theory via path integral, this path integral measure is not diffeomorphic invariance. So therefore, this partition function may not be diffeomorphic invariance. And so that's what we call the gravitational anomaly. And this kind of gravitational anomaly is always invertible. So that means that like this Jacobian is some kind of non-zero complex number. So these anomalies are invertible. And that's a more traditional point of view of anomaly. And but what we have here is a more modern point of view of anomaly. We say that anomaly is the abstraction to have a realization in the same dimension. But however, even anomaly theory can be realized as a boundary of a higher dimensional theory. And in this case, anomaly is really corresponds to topological order in one higher dimension. And from this point of view, we see that this anomaly is more general, and in particular, than in general non-invertible, because topological order in higher dimension in general not invertible. The stacking two topological order can never produce trivial states in general. And so therefore, so this more modern point of view really gave us more general gravitational anomaly, and in particular, non-invertible gravitational anomaly. The traditional gravitational anomaly, I think, may correspond to invertible topological order in the bulk. And so in the next, I'm going to try to using this idea of a topological order in gravitational anomaly to study a gapless phase. As I mentioned that the gapped phase are related to topology, which are easier. The gapless phase is a much more difficult question, and maybe represent a future direction. And here I want to say that there is one way to study gapless phase via gapped phase, in particular via this notion of a non-invertible gravitational anomaly. Actually, usually people say that anomaly don't contain too much information. Probably it's not enough to start using that to study gapless phase. But however, here I want to emphasize that this non-invertible gravitational anomaly actually contain a lot of information. So because it contains a lot of information, maybe it's possible to use this information to characterize or maybe even classify a gapless CFT. Okay. And for the convenience later, we'll also we also give this non-invertible gravitational anomaly another name called the categorical symmetry. The categorical symmetry is just another name for non-invertible gravitational anomaly, which is another name for topological order in one higher dimension. So actually, there's one object. We give three names, either topological order in one higher dimension, or non-invertible gravitational anomaly, or categorical symmetry. They all mean the same thing. And here I try to, in the next, we try to present the case. Maybe we can use this categorical symmetry to characterize and classify a gapless conformal field theory. Okay, and so this is really try to build a case for this statement. This may not be accurate, and maybe you need modification, but that's maybe a direction of effort. Okay, to really go into that direction, so let's remind you that remember that a two-dimensional 2+1D topological order is characterized by degenerate ground states, or in more detail by the modular matrix. This is a regenerative representation of a mapping class group of a torus. Okay. So here I want to explain a little more detail how to understand the degenerate ground state from categorical point of view. Okay, so it's convenient to consider space-time, which is a cylinder. So this M3 is a solid cylinder. It's solid cylinder. So here, this face and that face is identified. So this solid cylinder is our space-time. And the real direction is a time evolution direction. So they are Euclidean evolution. So when you have a Euclidean evolution for a long time, it's like projection to ground states. So therefore, this kind of state-time evolution on the solid cylinder produce a ground state on the surface of a cylinder, which is a torus. Okay, so this is kind of geometrical view to view the degenerate ground state on the torus via this evolution of represented by this solid cylinder in space-time. But however, this pure solid cylinder only gives rise to one ground state. How to get other degenerate ground states? And to get other degenerate ground state, we can insert the word line of a type I anion in the middle of a solid cylinder. Okay, which wrap around this S1 direction. Okay, and again, this time evolution is projection. That give you another different ground state because this insertion. So from here you can see that the different degenerate ground states are labeled by the anion type in the bulk, and then this ST matrix also is an index of ST matrix, also is anion type. Okay, and so this ST matrix labeled by anion type really gave this characterization of 2+1D topological order, or equivalently, it is a 1+1D non-invertible anomaly, or 1+1D categorical symmetry. So you'll say that what is a 1+1D categorical symmetry? How to label them, how to characterize them. I say, okay, SMT matrix, which is labeled this categorical symmetry. All this more precisely is a unitary modular tensor category, which is labeled a categorical symmetry in 1+1D. Okay, that's some background. Okay, so now let's try to explain why this 1+1D categorical symmetry can characterize or determine the 1+1D conformal field theory. Or another way to say how this ST matrix can characterize or determine 1+1D conformal field theory. And here I want to say that when you have a 1+1D conformal field theory, and it have a partition function defined on the space-time with some shape. So space-time is like a shared torus. Okay, the shape of space-time is parameterized by this complex number tau. So that kind of moduli space. Okay, and then the partition function actually is a modular invariant. And the modular transformation, they are invariant. Okay, so this is true for the partition function in 1+1 lattice model, 1+1D lattice model. So in some sense, we can say that the modular invariant partition function means anomaly free, means realizable as a 1+1D lattice model. So this modular invariance means anomaly free in 1+1D. But however, when you have a 2D topological order and consider it's a gapless boundary, if a boundary of a 2D topological order are described by conformal field theory, then this conformal field theory will be anomalous. Okay, and this anomalous conformal field theory actually have a multiple of a partition function. So it do not have a single partition function. The partition function have many components. Okay, Why is that? Because of the following. When you have let's using this a cylinder to represent space-time of a 2D topology order. The 2D topology live on the disk, and the vertical is time direction. Okay, and then this different partition function correspond to insertion of a anion in the middle of the in the middle. But this anion in the middle is far away from boundary. So in some sense, the boundary is still the same. But however, insertion of anion in the bulk change the boundary sector, actually gave us different boundary partition function. Okay. And so therefore, the different boundary partition function, again, labeled by an anion type in the bulk. Okay. And so this multi-component partition function actually very much similar to the degenerate ground states. You know, this graph and this graph is the same. It just rotate. We just rename y as t or rename t as y. It's just renaming these two labels. In the Euclidean space, you call this t or call it y, doesn't matter. So the degenerate ground state actually correspond to this multi-component partition function, and which in turn that we say that this multi-component partition function is modular covariant, and this modular covariance is a generalization of a modular invariance, and the modular covariance is characterized by this ST matrix, again characterized by this anomaly or this categorical symmetry. So therefore, using this modular covariant condition, we can determine the boundary partition function. So this is what I mean by using the bulk topology order, or using this non-invertible anomaly, or using this categorical symmetry to determine the boundary conformal field theory. Yeah, it's really using this kind of relation. So let's try to apply that relation in a simpler case. We consider the gapped boundary. For the gapped states, the partition function is a constant, do not depend on tau. It's topological, so it's a constant. And but in one dimension, this partition function turns out to be an integer. That has to be integer. Okay. So therefore, to obtain gapped boundary of a 2D topology order, we need to solve this equation and looking for the integer solution where the first component equal to 1. Okay, there's some normalization condition. Okay, and for the Z2 topology order, this two-dimensional gauge theory, this ST matrix is this two 4x4 matrix, and then we find two integer solution for this equation, and one is 1, 1, 0, 0 or 1, 0, 1, 0. And the first condition have an E condensation. Let me explain it a little bit. Why it have an E condensation? Because this Z1 equal to 1, they always equal to 1. Means we have the partition function just means you have a ground state on the boundary. That's ground state on the boundary is just 1. Partition function equal to 1 means you have a ground state with 0 energy. Okay. And however, if you insert an E on the middle, then you say that's impossible. We cannot create an E alone. So we can create a pair of E particle in the bulk. Then moving this bulk E particle to the boundary. If a boundary can absorb this E particle, then we arrive at a situation where we have a single E particle in the bulk. But another E particle is absorbed by the boundary. The boundary can absorb the E particle means E is condensed. So therefore, therefore we have a E appear in the bulk. The boundary is absorbed by a E, absorb another E, and so that's this one. But however, if you create M particle in the middle, you can also create a pair of M particle and moving M particle to the boundary. But this boundary cannot absorb M particle. So M particle appear as an excitation on the boundary, have energy. Then in the long time limit, this final energy gives rise to this zero partition function. So this zero means that the M particle is not condensed on the boundary. And this zero here means F particle is not condensed on the boundary. Only E particle is condensed on the boundary. Similarly, in this case, the M particle is condensed on the boundary, but the E and F particle is not condensed on the boundary. So there's only these two kinds of a boundary for this E2 topological order. Okay. And then using this example, I can explain why we call this anomaly as a categorical symmetry. Why we give another name? You know, you gave something known a new name seems to mean anything, but here giving a new name motivate us to thinking in new directions, and so it may mean something. Okay. So this new name, this categorical symmetry, this name really is motivated by the following thing. The 2 plus 20 topological order have a conservations. You know, E particle have a Z2 conservation because this Z2 fusion rule. The M particle also have a Z2 conservation because M particle also have a Z2 fusion rule. So therefore, there's a 2 conservation of in the 2 plus 1D Z2 topological order because the 2 fusion rule. Certainly you can say this F particle also have a Z2 fusion rule. That's another symmetry. But actually, because F is a bound state of E and M, so this one is not independent. It only have 2 independent Z2 fusion rule. In physics, when you have a conservation, we say there's a symmetry. So therefore, this 2 plus 1D Z2 topological order have a Z2 symmetry coming from a conservation of E and Z2 symmetry coming from conservation of M. So I have 2 symmetries. Okay. And however, on the boundary, because the boundary is coming from this E condensed. So that's why we have a spontaneous symmetry breaking. The condensation means a spontaneous symmetry breaking in physics. So therefore, it's like the bulk Z2 symmetry is spontaneously broken to the single Z2 symmetry of M conservation. But the other boundary, we have M condensation. So the other boundary can be viewed as a symmetry breaking of a Z2M. So only Z2E is preserved. So therefore, we can describing these 2 boundaries as a spontaneous symmetry breaking of a categorical symmetry. The boundary, they partially break this 2 Z2. Is the first one or second one. So therefore, calling gravitational anomaly or calling 2D topological order as a categorical symmetry is really motivate us to using this language, using symmetry breaking language to describe the boundary. But however, these 2 symmetry is not a direct product. So I'm using the V symbol to say there's some composition of 2 symmetry. The reason because this E and M particle have non-trivial mutual statistics. If you move E around M, they have a pi. They have pi mutual statistics. So therefore, these 2 symmetries are not independent. If E and M have a trivial mutual statistics, then these 2 symmetries will be independent. We will say this times Z2 times Z2. Because non-trivial mutual statistics, these 2 symmetries are a little bit special. In particular, because this non-trivial mutual statistics, we cannot break both symmetry together at the same time. We cannot break all of them together. We can only break one of them. Okay. So using this picture, we can say then that's for gap states. Then for the gapless states, using this picture, how to describe the gapless states. So here I want to say that the E condensed boundary and M condensed boundary, there's 2 gapped boundary. And there's a phase transition between these 2 gapped boundary. And the phase transition is a continuous and it's a critical point. This critical point is a gapless. Okay. So remember this, the E condensed boundary is that we break the Z2E symmetry. And the M condensed boundary break Z2M symmetry. But however, at this critical point, we don't have E condensation nor M condensation. So actually, this critical point have a full categorical symmetry, and so this is a point. So therefore, we can view this 1 + 1D CFT as a gapless space with a full categorical symmetry. Okay. And so this is really what we mean by this categorical symmetry can be used to determine or even classify CFT. Okay, so let's try that to see, is that really true? Can we use categorical symmetry to completely determine the CFT? So as I mentioned that this Z2 topology order or this Torah code model, whose categorical symmetry or 2D topology order are described by these two ST matrix. Okay, these two 4x4 matrix describing 2D topology order or categorical symmetry. Okay, and the gapless boundary would have a 4 component, and now because the gapless boundary, we are looking for the partition function which have tau dependence. And also, we're looking for the solution with no condensation, means that we're looking for the solution of this equation where every component is non-zero. So there's no condensation. Every component is 0. It's non-zero. Okay. And actually, we find that the solution of this equation is not unique. There's many solutions. So here is just 1. So both of these 4 component or characters of CFT character are solution of this previous modular covariant equation. The first one is a familiar one. It's called Ising CFT. The second one is a minimum model. This is a 5-4 minimum model CFT. Central charge is 7/10. Central charge here is 1/2. So we see that the correspondence is not 1-to-1. So, but we can improve it because you can see this solution is more special. It has a minimal central charge. The minimal central charge means the minimal number of excitation. So therefore, maybe a categorical symmetry can determine a minimal CFT, which is minimal central charge. And maybe this correspondence is 1-to-1, or close to 1-to-1. May not be exactly 1-to-1, but close to 1-to-1. So we are really trying to push in one direction, but we don't know exact result. But we hope we get something non-trivial here. So by choosing the minimal central charge, we hope to get a better 1-to-1 correspondence. Okay. So actually, this idea is put in a very general form in terms of topological weak rotation. Okay. So for every topology order, we can have a boundary which the boundary do not have any condensation. And this boundary is gapless. But certainly, simply saying the boundary have no condensation do not uniquely determine the boundary. Because you can always stack anomaly-free boundary to the boundary of a bulk. But we can, again, we can have additional requirement require the minimal amount of boundary excitation. Maybe there's a near 1-to-1 correspondence. And this is described as topological weak rotation. And so maybe one can using the 2D topology order or unitary modular tensor category to classify 1 + D rational CFTs. And but actually, there's another idea, again, using the symmetry. In some sense, the categorical symmetry can be viewed as an emergent symmetry of the Ising model. Okay, so let me come to this point. So we say that the critical point have this categorical symmetry. Means that it have a Z2 symmetry of conservation of E. And this is well known because the CFT of Ising model have Z2 symmetry because Ising model have Z2 symmetry. Their CFT of phase transition also have Z2 symmetry. Okay, but however, this statement really say that the Ising CFT also have emergent symmetry, have this additional Z2 symmetry, this Z2M symmetry. So in addition to Z2E symmetry, there's another Z2M symmetry in the icing critical point. And these two emerging symmetry is put together in some non-trivial way, which is called the categorical symmetry. So therefore, this categorical symmetry can be viewed as an emergent symmetry, which appears only in low dimension from this CFT. Okay. So then we can ask what is emergent categorical symmetry of this CFT, this icing CFT with the 4 component. Then obviously, as a simple, their emergent categorical symmetry is this Z2 topological order in 2 dimensions. But however, we can ask, do we have an even larger emergent categorical symmetry? You know, in physics, you may have emergent symmetry, but however, you may missing something. Means maybe actual emergent symmetry is bigger than you thought. Okay, certainly. So here we are asking the same question: do we have an even bigger emergent symmetry? So that's a renaming help us to thinking this way. Do we have a bigger emergent symmetry? Another way to say that, can we view this icing CFT as a boundary of a more complicated 2D topological order with more unknowns, or more generally, bigger total quantum dimension? Actually, I don't know how to define that in higher category, but at least in modular tensor category, we have this total quantum dimension. I assume something similar can be defined for higher category. So therefore, we want to view the icing model as a boundary of something more complex topological order. So they have a bigger categorical symmetry. Actually, the answer is yes. Actually, the icing model, this icing model, is a boundary of this, I don't know how to call this. There's a unitary tensor category, also called a unitary modular tensor category, also called icing, and is a conjugate. And this double icing have a 9 ions. So there's a 9 by 9 there's 9 component partition function, and which satisfy this modular covariance. So therefore, the icing CFT actually have a so-called emergent maximal categorical symmetry, which is given by this double icing model, a double icing of a modular tensor category with the 9 ions. Okay, so therefore, so this maximum categorical symmetry maybe is more useful. Similarly, remember this another solution of icing this modular covariance for the Z2 topological order. This is another solution, and this one is this minimum model of 7/10 central charge, and this one actually not only have this Z2 categorical symmetry, it actually have an even bigger categorical symmetry. Okay, this even bigger categorical symmetry correspond to the 2D topological order of this kind, you know. And the first one is a Fibonacci onion model, Fibonacci model we mentioned. It's also actually the G2 level 1 Chern-Simons theory. The second one is a twisted icing model. It's an icing unitary fusion category, but with some twist. And so tensor product of 2. And then the other one is a time reversal conjugate. So this kind of 2D topological order have a boundary given by this kind of minimum model CFT. So therefore, this minimum model CFT have a maximum categorical symmetry given by this kind of 2D topological order. So this really very suggestive. Maybe this is a better way to say that 1 plus 1 irrational CFT maybe have a 1-to-1 correspondence with a maximum emergent categorical symmetry. And so we can using the maximum emergent categorical symmetry to classify 1 plus CFT. And here I just want to mention that choosing the maximum emergent CFT is like choosing the smallest character. We're using this single character, this part, rather than some of these several characters, is a single character as the trivial component of partition function. And then because the trivial component is chosen to be the minimal character, then the partition function should have a more component to have modular covariance. Okay, basically that's the idea. And this way you get a maximum categorical symmetry. And so this idea may work in higher dimension. And we don't know, but this is really quite a jump. Whether in higher dimensional Laplace CFT, one can also define the maximum emergent categorical symmetry. Okay, so here, let's just consider an example. Let's consider a higher dimensional theory, like a 2-dimensional, 3-dimensional lattice model with a G symmetry. G is a finite group. Okay. Then this G symmetry breaking point have a phase transition. You know, this G symmetry breaking transition is described by the critical point. And this critical point should have a G symmetry. Okay. The critical point of a G symmetry break transition should have a G symmetry. Actually, in this paper, we show that it also have another symmetry. It's called the higher symmetry. But this is not really higher symmetry. It's a generalization of a higher symmetry. So we call this an algebraic higher symmetry. So this is some kind of algebraic higher symmetry. It's a generalization of a symmetry and a generalization of a higher symmetry. And this is not described by group because higher symmetry are described by higher group, but this one is not described by higher group. Okay, and so actually this critical point have this kind of a categorical symmetry. And this also works in 1+1D. But however, in 1+1D, this one is not maximum. But in higher dimension, we don't know, but this one may be maximum. So therefore, this symmetry breaking transition corresponds to this kind of a categorical symmetry. But as I mentioned, that categorical symmetry just means a non-invertible anomaly, or means a topological order in one higher dimension. So what is this topological order in one higher dimension, which corresponds to this kind of categorical symmetry? The answer is a G-gauge theory. So the topological order described by G-gauge theory is corresponds to this kind of categorical symmetry. Okay, so therefore we see that we have a relation between CFT and this categorical symmetry, means topological order in one higher dimension. And this relation is very much like ADS CFT duality. At least this CFT and this CFT is the same. And this ADS seems like a corresponding topological order in one higher dimension. So let's try to explore that connection. So what's the relation between categorical symmetry or non-invertible gravitational anomaly and the ADF CFT duality? Okay. So in the ADF duality, we have this following two statements. Okay. If at the boundary we have a G symmetry, then that means the ADS bulk would contain a G-gauge theory. That's one statement. Another statement is that if ADS bulk contains a G-gauge theory, then the boundary should contain a G symmetry. Okay, so that is a two thing people say in the ADS CFT duality. But however, what we try to say here is that it's something similar, but a little bit more precise, more tighter. You know, it's a tighter statement. And we say that if bulk have only gauge theory, but this gauge theory should allow charge fluctuation and flux fluctuation. So that is a gauge theory which allow charge fluctuation and flux fluctuation, and certain gravity. We always have a gravity in the bulk. So this particular, that's what we call pure gauge theory. If a bulk have this pure gauge theory, then the boundary is this particular critical point. this boundary CFT will be the CFT describing this G symmetry breaking transition CFT. Okay, so the pure gate theory corresponds to this G symmetry breaking CFT, and and also reverse also true, that is this symmetry breaking CFT at the boundary corresponds to pure gate theory in the bulk. Okay, so actually this is what we described. That is so the symmetry breaking transition CFT corresponds to pure gate theory in the bulk. Okay, but so in some sense, this ADF CFT structure describe how we transition from a boundary to the bulk. So actually this there's some layer boundary have the neighborhood. This boundary neighborhood probably is like this have this geometry of ADS structure, which is really describing this gaplessness of the boundary. So really come to this picture. So we have a CFT on the boundary, which actually this boundary CFT really characterized by this geometry, this lattice geometry. We'll go to further to the infinity, we get a bulk gap theory, which is a pure gate theory. So this is like a combination of these two pictures. So this is this ADF CFT connection. And so the bottom line is that maybe this a maximum emergent maximum categorical symmetry probably carry a lot of information. Maybe we can use that to classify, to characterize this gapless system. Okay, yeah, that's all. Thank you.
Well, thank you very much. So are there some questions for now? Otherwise, let me recall there will be this discussion session. And I suggest that Xiao-Gang goes to discussion session number 1 as yesterday. So any questions for now?
So maybe I just have a very quick question. So if this G n plus n minus 1, that's not a higher group, right? But
not higher group.
Still some sort of higher symmetry. What is that?
Okay. Yeah. Let me try to see. Okay. And okay. I'm sure you can write something. Okay. Yeah. So so usually when you have a symmetry, you have this U G, and then you multiply another U G prime. You get another transformation is U G and G prime. So that is a group-like symmetry. Even higher symmetry or higher form symmetry have this group-like relation. And but however, for this algebraic higher symmetry, we have algebra. So basically, we have the composition of two symmetry transformation, U and U prime, give us a sum of W plus W prime plus. There's a sum, okay. And so it's more like an algebra. And so actually this kind of symmetry is more like this kind of algebraic
so it's
symmetry.
this EF2
Yeah.
thing.
Hmm?
It's like the EF2 case.
Yeah, it's like a fusion category. You know, the ordinary symmetry composed like a pointed fusion category. But actually, that's maybe too much restriction. We could allow symmetry operation which compose as a more general fusion category, which contains sum. Yeah. So so this is called algebraic higher symmetry. Also, there's this kind of thing studied in 1+1 dimension CFT called the non-invertible defect line. Because in CFT, people study symmetry using defect line and non-inverted defect line in CFT also corresponds to that. So you can also call this a non-invertible symmetry. Or I think also some people call it maybe fusion category symmetry or something. You know, this it's something new, so there are different names. And in this paper, we call this algebraic higher symmetry.
I have a question. What is the precise mathematical definition of the V product in categorical symmetry?
No, there's no precise definition. This is really a physicist invention. It just say that because categorical symmetry is quite different from symmetry, but however, it has a parts which is very similar to symmetry. Say like this Z2 topological order, the conservation of Z2 charge is very much like ordinary symmetry, and the conservation of Z2 flux is like a ordinary higher symmetry. But when you combine them together as a Z2 gauge theory as a whole, then it's not quite a symmetry. It's really unitary fusion category or some higher fusion category, but it's a part really like a symmetry. So that's why we invent this name to emphasize it have a parts really like a physics symmetry. But this is really not a precise notation. And the full data is this a higher fusion higher category is the full data to characterize a categorical symmetry.
Excuse me, when G is abelian finite group, isn't that G n minus 1 is just a higher symmetry?
Exactly. So only when G is not abelian, it became algebraic higher symmetry.
I agree.
But if G is abelian, then everything can be rephrased within this higher form symmetry.
Thank you.
I also have a question. So you mentioned this conjecture that perhaps emergent symmetries in the bulk, they will classify CFTs on the boundary.
Yeah.
So part of the CFT data is the spectrum of anomalous dimensions. How would they translate, assuming it works? How would you read anomalous dimensions from your emergent symmetry?
Yeah, this is a very good question. So let me just clear this. Okay. So actually, let's say for this example, and we can see, yeah, from here we can see this relation. So this IJ are these three label of three anion in the Ising unitary fusion category. So this trivial object, there's a fermion, there's a sigma. So usually this is trivial, this is a fermion F, this is sigma, this is 1/16, this Ising anion. Okay. So from this relation, you can see that this topological spin of the anion in higher dimension happen to give rise to the fractional part of scaling dimension in the boundary CFT. Okay, so this connection is very direct, but however only the fractional part, the integer part of spin are kind of descendant field coming from derivative, and that part is not really captured. Okay, but the fractional part of scaling dimension is related to the topological spin.
Mm-hmm. Okay.
So there's a very direct relation. Yeah.
Mm-hmm. I suggest we just leave the session open as usual. So if you have more questions, please ask more questions. And otherwise, we meet again at 5:30 European time for the final talk of this session. And Xiao-Gang, thanks again for this wonderful mini course.
Thank you for organizing this meeting. Really, we see a lot of new faces. These are two different communities coming together. It's very exciting.
Thank you very much.
So I don't know, but Well, I don't know the physics, but it seems like isn't that like this algebraic symmetry that you just described? It looks like in our case the EF2 case, emergent fermion 2 case.
Maybe yes. Probably, yeah. It's like a EF2, and it's not pointed anymore. You know, the ordinary symmetry or higher symmetry, they're kind of like pointed. So their fusion always a pointed fusion. And this algebraic one just generalize that into non-pointed composition. And indeed, the EF2 case have also this non-pointed fusion. And it's related to that. And we need to generalize that because you know, this symmetry breaking for non-abelian group is a pretty common appearance in physics. But to really using emergent symmetry to describe that case, we have to generalize this symmetry to algebraic higher symmetry so that you can see this critical point have some kind of emergent algebraic higher symmetry.
Yeah, I guess it's my homework to understand this.
Can I ask some vague question?
Yes, please.
So how can I relate your story to the topological defect lines in CFTs? Say in Ising case. So usually in that context, the topological defect line, we consider the Ising CFT with the modular invariant partition function, and we still say that the Ising fusion category acts on the theory. So how can I relate that to your story?
Okay, yeah, and so okay, let me see. I can understand your question here. You can see here that the definition of partition function may be slightly different. So here we define partition function as a boundary of a bulk. So we specify the bulk. If bulk have no excitation, we only have this trivial component of a partition function. So yes. So we only have this part.
Yeah.
The bulk don't have a anion, we only have this part. But this part is not a modular invariant. And so to make a modular covariant, and we say that we insert an anion in the middle to obtain other component of a partition function,
yeah,
which actually correspond to the CFT with different defect line insertion. And we don't add them together, we just leave them alone as a different component. Then the whole thing became modular covariant. And this modular covariance actually is this ST matrix happen to correspond to the bulk topology order, what kind of anion you insert. Okay. But however, when you consider the so-called maximum categorical symmetry, we allow us to redefine the boundary sector. Usually the conformal field theory, their sector are specified. Here we say we don't specify sector in order to see even bigger symmetry. That is like in this case, if you want to see this this kind of Z2 categorical symmetry, we have a fourth sector. But we can see the bigger symmetry. We say, okay, let's assume consider CFT where whose partition function is given by this sector alone. Okay. Then you'll see that their model transformation require more component, and you get a more complicated topology order in one higher dimension. And this we interpret this phenomena as a bigger categorical symmetry. So that's a more emergent symmetry. And so this bigger categorical symmetry maybe carry even more information. So we are hoping maybe this maximum categorical symmetry carry more information, maybe it's closer to a classification. That's basically the idea.
Maybe I might be asking that how can I see the Kramer-Swanier duality from that categorical symmetry Z2 wedge Z2?
Kramer-Swanier duality basically is the exchange of E and M.
Yes.
It's this symmetry it's actually, I think it's realized in this case. So E and M exchange symmetry is contained in here. So in this case, in these two, the categorical symmetry, this Quantum wire duality is not incorporated. Let me explain what I mean. You can see those symmetry, those four components incorporated to Z2 symmetry because Z2 symmetry is a defect line at a boundary condition. That's what gave rise to four partition function. But the Kramer wire duality is act externally in this case, just exchanging E and M. So these four components do not change. But they do not appear as a defect line. So if you want to incorporate the Kramer wire duality symmetry as a defect line, you generate more component. And that gave rise to this 9-component partition function. So this 9-component partition function, the Z2M symmetry, Z2E symmetry, and the Kramer wire duality symmetry, all included as a defect line, as a boundary condition. So that's how we get a 9-partition function. So this one is included internally. So therefore, actually that's why we have even bigger categorical symmetry. So therefore, this is a very good question. This maximum categorical symmetry of Ising CFT actually contain Kramer wire duality symmetry.
I feel that somehow the Z2 gauge theory in the box should know the Kramer wire duality because that Z2 gauge theory have the symmetry exchanging the M and E and M, and therefore you actually have a surface effect. So,
no,
so
the Z2 gauge theory in the bulk don't have EM exchange as a symmetry, as a physical symmetry. It means the Hamiltonian have energy. As a topological theory, it have a symmetry. But as a generic topological order, the M particle, E particle may have a different energy gap. So they don't have that as a physical symmetry.
Yeah, but in the
you need to gauge. If you gauge this EM exchange, you get a double Ising model. After you gauge this EM exchange, then you force that to be a symmetry. So actually, that's another way to say that this double Ising model coming from the Z2 gauge theory after you're gauging the EM exchange symmetry. And this is really this after gauging, that became categorical symmetry. Before gauging, that means we overlook that symmetry. So because in physics here, when you see topological order, the topological kind of arbitrary Hamiltonian and not ideal Hamiltonian. So all these topological excitation may have different energy gap. So they don't have a symmetry unless you gauge them.
I see.
Xiao-Gang?
Yeah.
Xiao-Gang? Is the categorical symmetry somehow related to the quantum double?
Yes. So the categorical symmetry is actually categorical symmetry equal to topological order in one higher dimension, equal to unitary modular tensor category, and equal to quantum double in the gauge group sense. Yeah. So therefore, when you have this we have a group, the categorical symmetry is a quantum double of that group.
Mm-hmm.
Yeah, so that is so maybe that's a statement became much simple. That is at least in 1+1 CFT, which have a G symmetry breaking, their categorical symmetry is a G quantum double.
Okay, so may we say that the categorical symmetry is a sort of generalization of the quantum double?
Yes. So the quantum double is like a topological order in one higher dimension. So we can generalize that. So categorical symmetry also topological order in one higher dimension.
Okay.
Yeah. So in that sense, it's generalization. So like a categorical symmetry can be a unitary modular tensor category. So that's generalized quantum double.
So yeah, it's possible to give some formal definition of the categorical symmetry?
It's a topological in one higher dimension or non-invertible graphing anomaly. And then the next thing is how to define topological in one higher dimension, whether there is a more rigorous definition. Yeah, that became a pressing issue.
Yeah, I would like to view these things from the point of view of representation theory or generalization of representation theory.
Oh,
so
that'd be great. I don't know. Yeah.
Obviously, when we say quantum double,
yeah,
is the representation of some half algebra.
That's really great point. And
yeah.
So let me expand on this a little bit. So here we are talking about the categorical symmetry of Z2 gate theory, or this Z2 quantum double. Okay, and it have two representation, which is given by these two solutions.
Mm-hmm.
That's a gapped boundary is the simplest representation of this quantum double. But I don't know how to view that way. But I imagine there's a representation theory. One can find a representation of quantum double, and I can say this is the answer for that. In some sense, solving this equation is a little bit like looking for representation of the quantum double.
Okay.
Yeah, and the simplest representation is this. However, the more non-trivial one will be this infinite dimensional representation. Those are infinite dimensional representation because the conformal filter spectrum is infinite dimensional. So those are two infinite dimensional representation. And in this case, the different modules are grouped differently. You can see we group these two modules together as a single module. And this may not be necessary. We can look at this as a single module. Then it's a representation of, and view this as a non-trivial module. In this case, we get a bigger categorical symmetry. So actually, this representation can be viewed as representation of some bigger categorical symmetry. And that maybe you get more information. Yeah. So indeed it's this, but I don't know how to formulate that precisely. So that's definitely the direction. So view everything as representation theory. We have representation of a group symmetry, representation of a higher symmetry, and representation of a categorical symmetry, which can directly correspond to CFT. So this correspondence really is a representation of this categorical symmetry equal to CFT. We hope we have something like that. But I think we only have something very partial. That is, we view this deriving representation like solving this kind of a modular covariant equation. But we don't have a better way. And this is really, really important because in 1+ dimension, because partition function have this holomorphic structure, we know how to do this. In higher dimension, we don't have this holomorphic structure. We need something more. We don't know. So that's a bottleneck at the moment. Hopefully, there's a point of view of representation theory maybe can help us to have some idea. So this idea may even works in a higher dimension. Yeah.
Okay. Yeah.
That is
very good. You have
given
an excellent lecture. Yeah. I enjoyed it very much. Okay.
Can I add a few thoughts?
Yeah.
About the V product we propose, I think it want to give some sense that this say G V product, the G n minus 1, we want to say something like this G and G minus 1 are some sort of dual to each other. So if we start from, exactly. It's want to reveal there's a duality between these two parts.
Yeah, exactly.
So if we only know part of it, say we only know the Gn minus 1, there should be a way or a recipe to find out its dual. Then put the two together, we get this whole categorical symmetry.
Exactly. Yeah, this is a very, very good point. So maybe this notation do mean something. They maybe mean a lot. Okay, so this G like a E, like a charge. This is like a magnetic. So this G and a G n minus 1 is like a what do you call this? Magnetic duality, charge magnetic duality.
Yeah, electromagnetic
Oh,
duality.
electromagnetic duality. Yeah. So if you incorporate the electromagnetic duality, this notation probably became precise. Yeah. So this is this became, and also you can imagine, you can generalize. Maybe this one also is some kind of algebraic higher symmetry. Is electromagnetic duality is some other things. So this notation really means that this categorical symmetry have two parts, which are related by this electromagnetic duality. And then in this sense, this notation may become very precise and useful. Yeah, this is a very good point indeed, Wenjie.
Yeah, when the G is generalized from algebraic symmetry, it's going to describe by some higher fusion category. And usually there's notion of some dualizable fusion higher category. Then we need to find its dual.
Yeah.
And another thing, it's we mentioned that we can get this much for the 1 plus 1D case because the 1 plus 1D series has this holomorphic, anti-holomorphic separation. I think this in 3 plus 1D, there might be possible to generalize as well because there's some, say U1 theory, you can separate and they describe by some gauge field and
I see.
curvatures. They can be separated into self-dual component and anti-self-dual component.
Yeah, there's some kind of, especially that's another thought, a direction. If this holomorphic, anti-holomorphic can be have some higher dimensional generalization. And then we can just use the approach in 1 plus 1D to higher dimension. Yeah.
It's known that there's such a notion in 5 plus 1D.
I see.
In the context of the 2, 0 supersymmetric CFTs.
Yeah, in supersymmetric CFT, maybe there's such thing. So
but I think it's general too that in 5 plus 1D, such kind of holomorphic, anti-holomorphic decomposition exists. I don't know of the 4D or 3 plus 1D or other dimension generalization.
That when you have supersymmetry, maybe you can have this holomorphic, anti-holomorphic. So maybe using this idea, one can start in symmetric CFT. Yeah.
May I ask one thing?
Let me stop sharing. Yeah.
Oh.
Okay.
You
want to?
hi.
Okay. Yeah.
Yeah. Can I ask a quick question? So, is there any thought on how to do this with the continuous group? What would be the dual and what in general the structure would kind of look like? Okay, and I thought about it a little bit, and so here's my thought. And here I identify categorical symmetry as a topological order in one higher dimension. Yes. For continuous group, this identification probably should be abandoned. But however, the notion of categorical symmetry may still be useful. Right. We just view this as a ND property. I have certain relation or something constraint. But now we don't view this ND CFT as a boundary of N plus 1D CFT. Mm-hmm. Because for continuous group, their charge of flux, the flux is gapless. Yeah. But however, we can use it informally in a sense that maybe this N plus 1D topological order have certain limit and and physical limit which became a gap, like a velocity go to infinity. Oh, and then you can use that. But actually, maybe you don't need to use that. So actually, there's another motivation to have this new name, categorical symmetry. Mm-hmm. For finite group, it's identical to topological order in one higher dimension. But for continuous group, it may acquire life of its own. It's itself is a concept. It's not related to topology in one higher dimension, but it can be used in a similar way. I see. So that's what I'm hoping. So I do feel that for continuous group, you can use that in similar way, and but without interpretation as a boundary of a topological order.